Hello everyone and welcome to lesson number 30. Today we are going to be continuing with chapter 3, looking specifically at extrema on a closed interval. Let's start with the warm-up problem to remind ourselves what we were doing with the first derivative test in our last lesson. Here we want to find all the relative extrema of the function f of x equals 2x cubed plus 3x squared minus 12x. So let's use those same steps we were using last week, starting with finding the derivative. For the function f of x equals 2x cubed plus 3x squared minus 12x, our derivative, f prime of x, is just equal to, using the power rule, bringing that 3 down, you get 6x squared plus 6x minus 12. Once you found your derivative, you want to go ahead and find your critical numbers, which, remember, happen anywhere that your derivative is equal to 0 or at any of those problem areas like a vertical asymptote, a vertical tangent, or a cusp. Because we don't have a denominator here, we can pretty much just focus on setting our derivative, f prime of x, equal to 0. So we have 6x squared plus 6x minus 12 equals 0. Taking out that GCF, we get x squared plus x minus 2 equals 0, and factoring this, finding factors of negative 2 that add up to positive 1 would be positive 2 and negative 1. Setting each of those equal to 0, we get critical numbers at x equals negative 2 and x equals 1. Remember, with the first derivative test, our final step would be to test intervals around our critical numbers in our derivative f prime of x. So to do that, we set up our number line and we plotted our critical numbers, negative 2 and 1. From here, we identified numbers around or in those intervals. So let's plug in a negative 3, a 0, and a 2. Remember, you can plug in any numbers that are in those intervals. You don't have to do the same as me. We are testing these in our derivative f prime. So let's look at f prime of negative 3. Plugging into factored form, I get 6 times negative 3 plus 2 is negative 1, times negative 3 minus 1 is negative 4. Looking at the sign, I have a positive times a negative is going to give me a positive. Doing the same thing on my next two intervals, I have f prime of 0. Plugging again into factored form, I get 6 times 0 plus 2 is 2, times 0 minus 1 is negative 1. A positive times a negative stays negative. And finally, f prime of 2 gives me 6 times 2 plus 2 is 4, times 2 minus 1 is 1. Positive, positive, positive stays positive. Remember, we are looking for relative extrema, so we want to notice that our function would be increasing from negative infinity to negative 2, then decreasing from negative 2 to 1, and then increasing again from 1 up to infinity, which means that our function, f of x, is going to have a relative maximum here where x equals negative 2, and then it will have a minimum here where x equals 1. And then remember, that very final step was that we get to plug those back into our original function to find our ordered pair. So we want to look at f of negative 2, plugging into the original function that they gave us. You would have 2 times negative 2 cubed plus 3 times negative 2 squared minus 12 times negative 2, and you should get 20. And then f of 1, you would get 2 times 1 cubed plus 3 times 1 squared minus 12 times 1, and you should get negative 7. So our function f of x has relative max at the point negative 2, 20, and a relative min at the point 1, negative 7. So just a quick refresher of all of the steps we were taking last week to find the relative extrema on an open interval. Today we're going to be looking at finding extrema on a closed interval. The guidelines for finding extrema on a closed interval are a little bit different than the guidelines were for finding extrema on an open interval. That's because if you think about what we're looking for either the highest or lowest point on a graph, but when we have a closed interval, that means we only care between these two values. So the highest or lowest point will only occur either at those critical numbers, so at those places where we have that horizontal tangent, or at one of the endpoints. So the guidelines are a little bit different because we just have to locate all of those options and then actually test and see where we have the largest value and where we have the smallest value. So formally, it says to find the extrema of a continuous function f on a closed interval from a to b, our steps will be as follows. First, find our critical numbers, just like we have been in the past 2 lessons. So that means we're going to look for where f prime of x equals 0, so we still get to take the derivative, or where we have any of those problems, so the vertical asymptote, vertical tangent, cusp, etc. All of those things that we get from issues, usually with our denominator. After that, this is where it gets different. Once you find your critical numbers, now we're going to evaluate each of those critical numbers inside f, our original function, and then we're also going to evaluate each endpoint in f. So after you find your critical numbers, you evaluate in your original function f, and you're really looking for the greatest value as the maximum or the least value as the minimum. And just something to note here, on a closed interval, you're looking for your absolute minimum or maximum, so you should have just one answer for each. Okay, let's take a look at example 1. Here we want to find the absolute extrema of the function f of x equals sine of x on the closed interval from 0 to 2. So we're going to be following those guidelines for following a closed interval, finding extrema on a closed interval that we just went over. The guidelines start the same though. We have to start by finding our critical numbers, which we would do by looking for those horizontal tangents or vertical asymptote, vertical tangent, or the cusp. In this case, we're going to find our critical numbers just by setting our derivative, f prime of x, equal to 0. So let's start by actually finding the derivative of our function, f prime of x. If f of x is sine of x, the derivative of sine is just cosine of x. So setting that equal to 0, cosine of x equals 0. I did include the unit circle, or at least the quadrantals, over here on the right. Remember, cosine is our x value, so our x value would be equal to 0 here at pi over 2 and here at 3 pi over 2. So our critical numbers are x equals pi over 2 and x equals 3 pi over 2. That's the same. Now this is where it changes for a closed interval, because now we know that those extrema are either going to occur at the critical numbers or at the endpoint. So all we have to do now is actually evaluate the original function and see where we have our largest value and where we have our smallest value. So to do that, we're going to create a table and we're going to evaluate. So this was step 1. Step 2, we're going to evaluate our original function f of x, which means we are evaluating sine of x, and that is really the different part because we're going back to our original function, and we're going to evaluate that for our critical numbers, which was pi over 2 and 3 pi over 2, and our endpoints. When we say endpoints, we mean the endpoints of the interval that they gave us, so that would be 0 and 2 pi. So I'm going to set up a table so we know what we're evaluating here. So we're going to evaluate our endpoint, our function evaluated at 0, our critical numbers, pi over 2 and 3 pi over 2, and then our endpoints. So just to reiterate, we have our critical numbers here in the middle, and then our endpoints, and we are plugging all of those into our original function f of x equals sine of x. So now we just get to evaluate. So let's look at f of 0, which is just sine of 0 using our unit circle. Sine is our y value. Sine of 0 is just 0. F of pi over 2 would be sine of pi over 2, which is just our y value, which is 1. F of 3 pi over 2, which would be our y value at 3 pi over 2, which is negative 1. And then f of 2 pi, again, all the way around, this should be a 0. There we go. All the way around, our y value is just 0. So now that we've evaluated, we want to identify where is the greatest point, the maximum, and where is the least point, the minimum. So we notice that we have our greatest value here at 1 and our least value here at negative 1. So then we can say our function f of x has a maximum at the point pi over 2, 1, and a minimum at the point 3 pi over 2, negative 1. And then we just want to specify that we are talking about on the closed interval from 0 to 2 pi. Because we know that our sine function goes on forever and ever, and that is not our absolute maximum or absolute minimum on the whole function, but on the closed interval from 0 to 2 pi, we have the maximum at pi over 2, 1, and the minimum at 3 pi over 2, negative 1. Okay, we're going to follow the same process for example 2, finding the absolute extrema of the function f of x equals x squared minus 6x plus 2 on the closed interval 0 to 5. So we will start by finding our critical numbers. Again, there's no denominator here, so we really just have to focus on finding our derivative and setting it equal to 0. So let's find our derivative f prime of x using our power rule as 2x minus 6, setting that equal to 0. We get 2x equals 6 or x equals 3. So just the one critical number here. So then step 2 is to evaluate our original function at our critical numbers and at our endpoints. So we're going to set up our table. We want to evaluate at our endpoint 0, we want to evaluate at our critical number 3, and we want to evaluate at our endpoint 5. So we have evaluating at critical numbers and endpoints. Remember, we're plugging that into our original function f of x. So when we look at f of 0, we have 0 squared minus 6 times 0 plus 2 just gives us 2. F of 3 gives us 3 squared minus 6 times 3 plus 2 gives us 9 minus 18 plus 2 is negative 9 plus 2 is negative 7. And then finally f of 5 gives us 5 squared minus 6 times 5 plus 2 gives us 25 minus 30 plus 2 is negative 5 plus 2 is negative 3. From there, we're looking just for our greatest value and our least value. So our greatest value here would be 2, so here's our max, and our least value would be negative 7, so here is our min. So we can write our final statement. Let's start with on the closed interval. From 0 to 5, our function f of x has a maximum at the point 0, 2, and a minimum at the point 3, negative 7. Okay, example 3 is very similar. Here we are finding the absolute extrema of the function f of x equals 3x to the fourth minus 4x cubed on the closed interval from -1 to 2. So we're going to use that same process. Let's start by finding our critical numbers. And hopefully you have a good hang of this so far. There's no real denominator, so we can just look for where our derivative is equal to 0. So let's find our derivative, f prime of x. Using the power rule, we get 12x cubed minus 12x squared. Setting that equal to 0, we can factor out our GCF of 12x squared, and we're left with x minus 1 equals 0. So our critical numbers are just x equals 0 and x equals 1. Step 2 now is to evaluate our original function at our critical numbers, which we found as 0 and 1, and at our endpoints, -1 and 2, setting up our chart, f of -1, f of 0, f of 1, and f of 2. Remember, when we plug in, we are plugging into the original given f of x function. So we're looking at f of -1 is 3 times -1 to the fourth minus 4 times -1 cubed. This gives us -1 to the fourth would be a positive 1, so we have 3 minus -1 cubed is negative, so this becomes -4. 3 minus -4 would give us a positive 7. F of 0 would be 3 times 0 to the fourth minus 4 times 0 cubed. 0 to any power is just 0, which means that we just get out 0. F of 1 would be 3 times 1 to the fourth minus 4 times 1 cubed, which gives us 3 minus 4, which is -1. And finally, f of 2, and I'm out of room again. F of 2 gives us 3 times 2 to the fourth minus 4 times 2 cubed. 3 times 2 to the fourth minus 4 times 2 cubed should give us 16. Now looking for our minimum value and our maximum value. -1 was the smallest value we got out. That makes it our minimum. 16 was the largest value, which makes it our maximum. So we can write our final statement, and I'm going to come over here to do so, that on our closed interval, and that's a lot to write, but it's important, from -1 to 2, our function f of x has a max at the point our maximum is at 216, and a min at the point 1, -1. Okay, just 2 more for today, but we are going to look at 2 that are a bit more interesting. Directions are the same. Find the absolute extrema of the function. Here we have a function f of x equals 2x minus 3x to the 2/3, and then we're looking at the closed interval from -1 to 3. So just like before, we're going to find our critical numbers, which we need to do by finding our derivative. So here we would take our f prime of x as 2 minus, forgot my equal sign, 3, bring down that 2/3, we get 2x to the 2/3 minus 3/3 is -1/3. So we want to go ahead and simplify this. So let's make this say 2 minus 2 over x to the 1/3, and then finding that common denominator, x to the 1/3 over x to the 1/3. We can write our derivative, f prime of x, as 2 times x to the 1/3 minus 1 over x to the 1/3. Now our critical numbers will happen anywhere where this is equal to 0, so setting the numerator equal to 0, and then also because we have that denominator, that's where we would have some kind of issue, vertical asymptote, vertical tangent, or a cusp. So let's start by setting this 2x to the 1/3 minus 1 equals 0, and we get x to the 1/3 minus 1 equals 0, x to the 1/3 equals 1. Cubing both sides, we get x equals 1. And then also setting this denominator equal to 0, x to the 1/3 equals 0, cubing both sides, we get x equals 0 cubed is just 0. So two critical numbers, don't forget to set that denominator equal to 0 as well. From there, we want to evaluate our original function, f of x, at our critical numbers and also at our endpoints. So let's set up our chart. We want to evaluate at our endpoint -1, our critical number 0, our critical number 1, and our endpoint 3. Plugging into the original function, which was 2x minus 3x to the 2/3 power, if we look at f of -1, we get 2 times -1 minus 3 times -1 to the 2/3 power. 2/3 power is really the third root of -1 squared. -1 squared is +1, third root is still 1, so we would get -2 minus 3 gives us -5. F of 0 is 2 times 0 minus 3 times 0 to the 2/3 power. 0 to any power is just 0. 0 minus 0 stays 0. F of 1 would be 2 times 1 minus 3 times 1 to the 2/3, which just gives us 2 minus 3, which is -1. And then the hardest one, f of 3, we would get 2 times 3 minus 3 times 3 to the 2/3, and I'm going to reach for my calculator for this, and we should get -0.24. Remember, all we care about is where is the greatest value and where is the least value. So our greatest value, -5, 0, -1, and -2.24 is actually 0. So it would be our max. And our smallest value here happens at -5. This would be our min. So we can write our final statement on the closed interval. From -1 to 3, our function f of x has a maximum at the point 0, 0, and a minimum at the point -1, -5. Okay, for our final example, example number 5, we want to find the absolute extrema of the function f of x equals the square root of 16 minus x squared. And what's different about this problem is that we weren't given a closed interval, but there's a hint. It says consider the domain of the function to determine the closed interval. So if we think about the square root of 16 minus x squared, we know we cannot put a negative value inside our square root. So our domain of this function, thinking about the zeros of the inside, 16 minus x squared equals 0. We know that the domain of this function would be all values between -4 and +4. So we can think about the closed interval because this function only exists between -4 and +4. So once we've determined our closed interval, now we can go ahead and do this the way that we would do the first 4 examples. We want to find our critical numbers, which means we need to find our derivative. So our function f of x equals the square root of 16 minus x squared, which I'm going to rewrite as 16 minus x squared to the 1/2 power, because now when I go to take my derivative, I recognize this as a chain rule problem. So my derivative f prime of x equals, bringing my 1/2 down, leaving my inside the same, and then taking this to the 1 less power times chain rule needs the derivative of the inside, which would be negative 2x. So just simplifying this, my 2's cancel. I'm left with negative x over the square root of 16 minus x squared. From there, we need to locate our critical numbers. So we can set our numerator equal to 0, and we can set our denominator equal to 0. Setting our numerator equal to 0, we get negative x equals 0. So x equals 0. Setting our denominator equal to 0, the square root of 16 minus x squared equals 0. Whoops. Squaring both sides, 16 minus x squared equals 0. We probably already recognize that we are going to get x equals plus or minus 4, the same as our endpoints. So when we go to evaluate our step 2, our function at our critical numbers and our endpoints, we have these critical numbers are the same, so we really only have to evaluate at 3 locations, negative 4, 0, and 4, plugging into our original function, the square root of 16 minus x squared. If we plug in f of negative 4, we get the square root of 16 minus negative 4 squared, which just gives us 0. If we plug in 0, we get the square root of 16 minus 0 squared, which is the square root of 16, which is just 4. And if we plug in a 4, we get the square root of 16 minus 4 squared, which is 0. So this one's a little bit different because our maximum value happens here at 0, 4, but then our other 2 values are the same, so they're actually both going to be minimums. And if we think about the graph of this function, I'm going to come over. I'm running out of room. Over here is fine. If we think about the graph of this function, the square root of 16 minus x squared, what this really looks like is like so. So we can see how both those 2 points, negative 4, 0 and 4, 0, would both be minimums. So we can write on the closed interval negative 4 to 4, our function f of x has a max at the point 0, 4, and minimum points at the point negative 4, 0, and 4, 0. Sorry for squeezing that in at the bottom there. Okay, great job with this section with finding extrema on a closed interval. Homework 31 is on page 167, numbers 19, 21, 23, 25, 33, and 35. If you have any questions or need any help, you can go ahead and just reach out to your teacher.